While discussing about the first order and second order differential equation, you must have observed the letter E in the general solution. The letter E is also known as the Euler's number and is used as the base on natural logarithm. Some even call it an irrational number. E is named after the Swiss mathematician Leonhard Euler. In this video, we will first try to explain the mathematical interpretation of E and then move on to explain the economic interpretation. Consider a magical case where your money doubles every year. Suppose you have 1 rupee with you and this doubles next year. You will have 2 rupees with you next year. The 2 rupees when doubled becomes 4 rupees and 4 rupees when doubled becomes 8 rupees. Can you think of a mathematical expression for this increasing value of your money? You can express this increase in value in terms of the power of 2. First year it is 2, second year it is 2 square, that is 4, and third year it is 2 cube, that is 8. So if you want to find out the amount of money you will have after n years, when your money doubles every year, you can use the formula 2 to the power n. This situation may also be interpreted in a different form. Since your 1 rupee became 2 rupees, you can say that there was a 100% increase, or 1 plus 100% of 1, that is 2. In the second year, 2 rupees increased to 4 rupees. So, you may write 2 plus 100% of 2, that is 4. This means when the value is doubled, it means there is 100% growth. But in this case, we assume that money doubles on the last day of the first year and doubles on the last day of every year. This is actually not the case. Now, let us divide a year into 2 parts and distribute the 100% growth into 50% for 6 months each. What will be the value of 1 rupee after 1 year? After 6 months, 1 rupee will become 1 plus 50% of 1, that is 1.50. In the next 6 months, 1.50 rupees will become 1.50 plus 50% of 1.50, that is 2.25. This process can be mathematically expressed like this. This means the growth rate is divided into half over 2 time periods. Suppose you want to find the quarterly increase in your money. Divide a year into 4 parts and divide 100% into 4 parts, that gives 25% in each quarter. Can you calculate the value of 1 rupee at the end of the year? The formula will now be written like this. That is 100% divided into 4 parts for 4 time periods. Therefore, 1 rupee at the end of a year will be rupees 2.44. Similarly, this will be the formula if 100% growth rate is divided every month, and 1 rupee will become rupees 2.61 at the end of the year. And if the growth or interest rate is given every day, then the formula will be written like this. and 1 rupee at the end of the year becomes 2.714. In our example of rupee 1, 100% is nothing but 1 rupee. So, the general formula for n time periods will be written like this. Let the value of 1 rupee be y. Therefore, putting different values for n, we get different values for y. If n is equal to 1, y is equal to 2. If n is equal to 2, y is equal to 2.25 and so on. You can see that as n increases, y also increases. Does this mean that y will keep on increasing? You will observe that the value of y increases but converges around the number 2.71828 and so on. So, you cannot expect to get unlimited money. It converges around a constant. This constant was named by Leonhard Euler as E. Now, we are comfortable to define E. E is the maximum possible value that can be obtained after continuously compounding 100% growth for one time period. Mathematically, E may be expressed in this form. How do we represent a situation with growth rate of m% that is continuously compounded for t time periods? This is given by e to the power mt. In economics, this number or the value of E can be interpreted as the result of a special process of interest compounding. Compound interest or interest compounding is the interest calculated on the principal, which includes all the accumulated interest of previous periods of a loan or any deposit. The expressions e to the power mt, a into e to the power t, and a into e to the power mt are economically interpreted as continuous interest compounding. However, this is not an exclusive interpretation and it can be applied to the growth of population, wealth, or real capital.